What's up, everybody? My name is Eric. Welcome to my channel, Eric the Tutor. I'm going to be focusing on topics such as biochemistry, physiology, and organic chemistry. Today, we're going to be focusing in on biochemistry, and specifically, let's look at enzyme inhibition. Now, how do you control the activity of an enzyme? Well, you can control the activity by changing the concentration of active enzyme. Now, how can we do that? So we can change the actual concentration of the enzyme, or we can change the activity of the enzyme with inhibitor. Let's briefly touch on irreversible inhibition. This is basically the active site being unavailable for a prolonged period of time, such that the enzyme is altered in a way where it can't carry out its function to give you the product. Now, we're going to focus on reversible inhibition. So we have three types: competitive, non-competitive, and uncompetitive. We're going to focus now on competitive. Substrate and inhibitor are competing for the same active site of the enzyme. Now, if we have so much more substrate than we do the inhibitor, then the substrate concentration can essentially compete out the inhibitor. So, there would be no change in Vmax. Now we're going to go ahead and look at two plots. On our left, we have the Michaelis-Menten plot, and on our right, we have the lineweaver-burke plot, which is the reciprocal plot of the Michaelis-Menten equation. Our Km is labeled. Our Km represents the substrate concentration at which we are at 1/2 Vmax. And our Vmax is labeled. We see on our lineweaver-burke plot that we have a reciprocal plot, which is 1 over Vmax, and we have 1 over Km. Some limitations of the Michaelis-Menten plot is that V0 never reaches Vmax, and the initial slope is difficult to pick out. We decide to use the lineweaver-burke plot if we want to determine more accurately the Vmax and the Michaelis-Menten constant. Now, let's go ahead and look at what happens when competitive inhibition takes place. We see that our Km increases and our Vmax is unaffected. Notice how the Km changed on our lineweaver-burke plot. Now, when the Km increases, that means our affinity for the enzyme to bind the substrate is going to decrease. It makes sense that the affinity for the enzyme to bind the substrate decreased because the inhibitor is present at that active site. So the enzyme has no desire to go out and have substrate bound to it when there's inhibitor bound to it. Now let's go ahead and look at the enzyme plus a substrate form an enzyme-substrate complex, which then goes on to give you product. You can see that when inhibitor is present, the enzyme and the inhibitor will form an enzyme-inhibitor complex. And the Ki represents the dissociation of the inhibitor and enzyme complex to give you the enzyme and the inhibitor. This is competitive inhibition. It can be overcome by increase in the substrate concentration. Now we're going to go ahead and jump into non-competitive inhibition. Non-competitive inhibition is interesting in the fact that the inhibitor can bind the enzyme or can bind the enzyme-substrate complex to prevent the formation of product. Now, non-competitive is also different than competitive in the fact that non-competitive binds at an allosteric region, whereas competitive bound at the active site of the enzyme. Now, the inhibitor binds the enzyme regardless if there's substrate bound or not. So you can see on the left that there's no substrate bound in the enzyme. The inhibitor still binds to the enzyme. And in our second column there, the substrate is bound, and the inhibitor can still bind and prevent the formation of product. Now, the inhibitor decreases the turnover number, which is also represented as the kcat. We're going to go ahead and draw the Michaelis-Menten graph, and we're also going to go ahead and draw the lineweaver-burke and do a compare and contrast. So let's go ahead and do that. Our Km is going to stay the same. Our Km is unaffected here. And that's because the enzyme can still bind equally to the substrate, regardless if there's an inhibitor bound or not. So the inhibitor does not affect the substrate, and the substrate does not affect the inhibitor. They act independently of each other. But we are still not getting the formation of product, so this is essentially lowering our Vmax. Vmax is affected because the enzyme cannot turn over substrate into product. We're now going to move on to uncompetitive inhibition. Now, uncompetitive inhibition is different from non-competitive inhibition, such that the inhibitor can only bind to the enzyme substrate complex. It cannot bind to both the enzyme or the enzyme substrate complex. It binds allosterically at an allosteric region of the enzyme after the substrate induced a conformational change in the enzyme. So the inhibitor can fit and form a ESI complex. So binding the substrate induced an allosteric site that was not previously there. And at that allosteric site, the inhibitor binds the ES complex only. So I'm going to go ahead and draw this. Here it shows the enzyme inhibitor forming. Let's go ahead and compare and contrast the Michaelis menten versus the lineweaver burke. So here's our Km, our 1 minus 1 over Km, 1 over Vmax and Vmax. So we see that our Km decreases and our Vmax decreases. Now, why do you think that the Km would decrease? This comes down to Le Chatelier's principle. If the formation of enzyme inhibitor increases so much, then it's going to drive the reaction the other way to increase enzyme substrate formation. So you can see we're going to increase enzyme plus substrate. So the affinity of the enzyme for the substrate is large. Our Vmax decreases because the enzyme cannot turn over substrate into product as well. That concludes our discussion on comparing and contrasting the 3 different types of inhibition. Thank you guys for tuning in, and I look forward to seeing you guys next time.